Hello class, I wanted to talk today about how to do an axial force design problem. So we have a structure supported on either end by some rods, and those areas for those rods are given to us, and we have a maximum stress. We're trying to figure out what is the maximum load that this thing could carry. And this is kind of a triangular load. What is the maximum value of that triangular load over here at the point C? All right, so there's actually 2 or 3 different ways to solve this. Design problems, you can approach them from different ways. The big thing to remember here is the only bad assumption that you can make is that the left and the right side fail at the same time. That's our goal, is to figure out which one of these fails. If we know which one of these failed first, we have a better idea of what's going on. Now you might, if this was a uniform load, it'd be pretty clear that the one that was smaller would fail first, right? It would be this one over here. But because this is a triangular load, we're seeing more load on this side and less load on this side. But we have a bigger section here because the area of that section is 15 millimeters squared, and this is an area of 10 millimeters squared. So we have to figure out which one fails first. That's our goal. Fails first. So let's do the first method. The first method, I like to call this solving in terms of P. This is solving in terms of P. Basically, I'm going to go assume my W max is some sort of load, right? I'm going to say this is a constant. I'm going to solve everything in terms of that W. If I have an idea of what that is, I can figure out which one fails first. So let's solve in terms of P. The first thing I need to do is draw a free body diagram. The free body diagram for this is really simple, so I'm just going to draw it on top of this one. And that's okay for this particular case, because I know both of these are going to be tension. I'm basically going to cut the supports and say, what are those 2 tensions? If I know those tensions, I can figure out what's happening in the structure. So to find those tensions, I'm going to take a moment about A. I'll take a moment about A. Now, to do that, I need to figure out what this distributed load is. So to figure out what this force is, I know that I need the area under that triangle. Now, W max is our height. Our length is 6 meters. So I'm going to use those 2 quantities here to figure out what F is. F is 1/2 times base. Our base is 6 meters times our W max. And I'm going to assume that our W max is going to be in terms of, let's make it kilonewtons per meter. I like to assume units here. That makes it easier on me. So when I start calculating this, I'm going to get something that makes sense. So this is going to look like 3 times W. I'm going to drop the max here just for ease, but W or W max. And I'm going to make that 3 times W, and this is going to be in kilonewtons. All right, and what's the distance here? Well, I know that this is going to act from the fat end. That's going to be 1/3. So this distance here that I've marked from F to where D is, that's going to be 1/3 of our height, or sorry, 1/3 of our length here. So that'll be 2 meters. So this distance here, to take our moment about A, is actually going to be 4 meters. So I've got 3 times W times our distance of 4 meters. And if we think about that, that's going to create a negative moment. And then I've got, over here, I've got the tension in CD. And that's acting the opposite direction. Its distance is 6. So now I figured out, okay, well, that means that TCD is going to look like 3 times 4, that's 12, divided by 6. This is going to be 2 times, or sorry, it's 12W. 2W, and that answer is going to be in kilonewtons. If this is 2W, and our total is 5W from doing sum of forces in Y is 0, I've got tension AB acting up. I've got TCD, which I said is, in terms of W, is 2W. And then I've got the force from the distributed load, right? I could also call this a force resultant. That's probably a better idea. Let's change that to force resultant. Our resultant force is 3W. So this is going to be minus 3W, which means TAB is just going to be W. So based on that, I can then do a comparison. I now know these in terms of W, so I need to figure out which one fails first. Let's assume TCD fails first. Now, looking at this, I can actually figure out that that's going to be the case. If this is 2 times W, this is carrying twice the load that this one is. If we look at the areas, ACD is not twice as big as that. So I actually have a pretty good idea of what's going to happen there. I'm feeling that's going to be a pretty good guess. If I assume that TCD fails first, that's going to tell me what's going on. So TCD, we said, was 2 times W in kilonewtons. So if we assume that TCD fails first, then TCD, that we're going to know it's stress, right? And that's going to be area, right? We said, hey, TCD is going to be at sigma stress, the maximum stress, and our area is going to be the area of TCD. So I can actually rearrange this a little bit. I can then figure out TCD is going to look like that sigma max times the area of TCD, which is a pretty easy calculation, right? I said, okay, well, that's going to be 300 kilopascals times, we're going to say the area, and that is 15 millimeters squared. And I like to be clever in this case. I know that this is 10 to the third pascals, and I know that that is 10 to the negative third twice. So this is 10 to the negative 6. This is 10 to the negative 6. I know that this is going to look like 300 times 10 to the negative third. I've got pascals times millimeters, or I've converted it to meters by doing the 10 to the negative 6. So that's going to be in newtons. So I've got 300 kilopascals times 10 to the 15 meters squared. So I'm saying, okay, well, that stress then is going to be that's going to give me 0.3 newtons. All right, I made a small error here. I just wanted to correct that. You'll notice that I did 300 times 15, and I didn't actually multiply those two. Let me fix that. So 300 times 15 is going to be 4,500. Wondering why this was so small. This is 4,500 times 10 to the negative 30, 10 to the negative 3 newtons, or 4.5 newtons. This is a very small area, right? That's going to be in millimeters squared. So if that was a round bar, that's a very, very thin tension cable. So that's 4.5 newtons. That's going to be TCD. So I wanted to work backwards. I can rearrange this now that I know what the tension is, assuming that that fails first, which is our good estimate, right? We made a comparison of our areas. Which area is larger? This one's not larger by a factor of 2. So if the force is bigger by a factor of 2, we know it's going to fail first. So we know that TCD is going to fail first, which means, hey, our weight, if we calculate it using this, we said weight is going to be TCD divided by 2. And remember, when we set this up, we said TCD was going to be in kilonewtons per meter. So rearranging this, we say, hey, okay, that's going to look like 4.5 divided by 2. This would be 2.25 newtons. All right. So now we know what our maximum load is. And we could go back and check what that would be, but we could see that TAB is going to be much, much smaller by comparison. And we know that TCD is going to fail first.